TLevel, Digital Production, Design and Development, tlevelresources.co.uk. Problem solving. What is it? Problem solving refers to the process of designing solutions to computational problems. It involves analyzing a given problem, developing an algorithmic approach, and implementing it using appropriate programming techniques. Problem solving in computer science often requires logical thinking, algorithmic design, and programming skills. Problem solving subcategories: computational thinking and algorithms. 1.1 Computational thinking. Computational thinking is a problem-solving method that involves logical processing, abstraction, decomposition, and algorithm design. It's fundamental to creating computer solutions. Computational thinking is a way of thinking about problems that are similar to how computers think. We break down a problem into smaller steps until it can be solved. School is not one big problem. School is broken down into smaller sections to allow us to manage each section individually and then bring them back together. The four key components of computational thinking: decomposition, pattern recognition, abstraction, and algorithm design. Problem solving importance. Problem solving is important because it helps computer scientists develop software and systems that are efficient, reliable, easy to use. By breaking down complex problems into smaller subproblems and developing effective solutions, computer scientists can create software and systems that meet the needs of users. 1.1 Be able to use top-down, bottom-up, and modularization approaches to solve problems. Top-down problem-solving approach. Identify the main problem. Break it down into smaller subproblems. You then solve each subproblem in turn until you have solved the entire problem. Top-down approach is useful when you have a clear understanding of the problem and can easily identify its subproblems. Like writing an essay by outlining sections first. Bottom-up problem-solving approach. Identify the simplest subproblems and then gradually build up to solve the larger problem. Bottom-up approach is useful when you have a complex problem and are not sure how to break it down into smaller subproblems. Like assembling a jigsaw puzzle. 1.1.2 Be able to decompose problems. Identifying and describing the main features of a problem or process. Breaking a problem down into smaller, more manageable parts. Modularization. Modularization is breaking down a program or problem into independent, interchangeable modules. Like car manufacturing, where each part is separately produced. Why modularize? Modularization is important because it allows you to break down a large problem into smaller, more manageable parts or modules. This makes it easier to understand and solve the problem, as well as to test and debug the solution. By breaking the problem down into smaller parts, you can also work on each part independently, which can save time and reduce the complexity of the overall solution. Decomposition and modularization. These words are sometimes used interchangeably, meaning you can swap the words out. Problem decomposition. For example, if you were trying to build a house, you would break down the problem into smaller subproblems such as designing the floor plan, laying the foundation, framing the walls, installing the plumbing and electrical systems, and so on. Each of these subproblems can then be solved independently before being integrated into the larger solution. 1.1.3 Be able to use pattern recognition. Identify and describe trends and similarities within and between problems and processes. And to identify and describe common features between a given problem and existing solutions. Make predictions and assumptions based on identified patterns. Pattern recognition. Pattern recognition is identifying and understanding trends or regularities in data. As in problem solving, it helps detect similarities and differences between problems, streamlining solutions and predicting outcomes. It identifies commonalities between problems and existing solutions, aiding in solving similar problems, like recognizing patterns in customer behavior to predict future trends. Pattern recognition example. Let's say you're trying to identify a pattern in a sequence of numbers. Even numbers could be 1, 3, 5, 7, and 9. By recognizing that the difference between each number is 2, you can predict that the next number in the sequence is 11. This is an example of pattern recognition because you're identifying a trend in the sequence and using it to make a prediction. 1.1.4. Be able to use abstraction and identify information that is needed to solve an identified problem, and filter out unnecessary details at different stages of a problem, and create a layer of abstraction appropriate to the stage in the problem-solving process, including what inputs are needed and what the expected outputs are, things that will vary, things that will remain constant, the key actions the program must perform, and repeated processes the program will perform. Abstraction. Abstraction is simplifying complex systems by focusing on crucial details and ignoring unnecessary ones. It's essential in problem solving for identifying critical information and reducing complexity. A layer of abstraction is a way of hiding the complexity of a system by providing a simplified representation of the problem at hand. Abstraction involves focusing on essential details and omitting irrelevant ones in problem solving. Identify necessary inputs, expected outputs, variables, constants, key actions, and repeated processes. For instance, when building a ticket booking system, key details include movie selection, timing, seats, payment, and confirmation, while other details like cinema decor are irrelevant. When building an online ticket booking system, the abstraction process helps you understand what you need to focus on. Unnecessary details, such as the color of the cinema's walls, the type of seats, or the brand of the projectors, can be ignored in this context. The inputs: customer's choice of movie, date, time, and number of tickets. Outputs: confirmation of booking with details such as the movie name, date, time, and seat numbers. Movie choices: available dates and times, number of available seats, the process of selecting a movie date, time, and number of tickets, payment process, ticket confirmation process, e-selection of movie, date and time, number of tickets, processing payment, and confirming the ticket, and acting processes. This would be the process a user goes through for each booking. Abstraction example 2. If you're trying to solve a problem involving a car, you might focus on the car's engine and how it works, while ignoring details like the color of the car or the type of seats it has. By focusing on the most important details, you can simplify the problem and make it easier to solve. Abstraction example 3. If you're trying to navigate a city using a map, you might focus on the major streets and landmarks while ignoring details like the names of every building or the exact location of every park. And by focusing on the most important features, you can simplify the map and make it easier to use. This is the first part in the series for TLevel digital production, design, and development. Thank you for watching. Stay tuned.